the last thing we have left to do with quadratics is called curve fitting. Okay, so what we're doing is we're going to try and map data to a specific quadratic equation, right? We're going to use the regression. We've already done linreg, where we did linear regression. Now we're going to do quadreg, where we do quadratic regression. And that's a really calculator-heavy thing, so we're actually going to talk about that more in class. But we're at least going to talk about some more of the algebra side of it before I totally launch you in there. Okay, so this is the last section in Chapter 5. Talking about how we can map or how we can work with data that represents a quadratic equation. First thing we have to know is, how do we know if it's going to be a quadratic or not, right? And in order to identify, to tell whether quadratic or tell whether a set of data is quadratic, we calculate the second differences. And we'll look at what that means. But what we need to show is, if the second differences are equal, well, then we have a quadratic, or data x and y's that represent a quadratic equation. So let's look at our first example. We have 5 ordered pairs here: 311, 421, 535, 653, and 775. Okay? So what we need to look at here is, how can we show whether this is quadratic? The first thing we do is we calculate the first difference, right? 21 minus 11 is 10. 35 minus 21 is 14. 53 minus 35 is 18, and 75 minus 53 is 22. Now, as we look at this, the first differences are not equal. The x's are equally spaced: 3 to 4, 4 to 5, 5 to 6, 6 to 7. Okay, those are equally spaced. But right now, the first difference is not equal. So we can't say anything yet, so we calculate the second difference. 14 minus 10 is 4. 18 minus 14 is 4. 22 minus 18 is 4. When we look at those second differences there, we see that the second differences here are all 4. That's awesome. That means that this data, these 5 ordered pairs, represent a quadratic equation. That's what this is saying. It doesn't tell us what the quadratic is. It doesn't give us a ton of information, but it does tell us that we can represent this with a quadratic, with an x squared equation. Okay? Let's look at another one. I'm going to give you this one. I want you to try it. Okay? Draw that little table, start calculating some differences. You can do this. I'm going to tell you right now that for sure the x's are equally spaced. They're spaced by -1. -1, -1, -1, -1. It's negative, but it is equal spacing. Okay? So what did you come up with? Did you notice that when you did this, you should have seen, or I hope you noticed, that everything was 2. And some of you are maybe like, yeah, 2, second, 2 means second, but that's not what I'm getting at here. I'm on the first layer of arrows. You see that? That's the first layer of arrows here. That means I've only calculated the first difference. And here the first difference is constant. That means this is actually linear data. If it's the first difference, it's linear. Second difference is quadratic. And I'm sure you can guess that if it goes all the way down to the third difference, then we're actually looking at cubic. Okay? This is not a quadratic. This data, these ordered pairs, do not represent a quadratic equation. They don't have equal second differences. Okay? This actually is a line, I've said that already. This line has a slope of -2. That's one of my favorite things about this difference idea, right? This difference is 2, this is -1, so my slope is 2 over -1, which you all would know as -2, right? Change in y over change in x. Either way, boo, not a quadratic. Now, with this idea, we can take it one step further. I'm telling you right now that this represents a quadratic, but what does x at 0 have to be in order for this to be a quadratic? Now, f at 0 is right here. This value in this gray square is the function evaluated at 0. What would that equal? So we start with this. We start by figuring out what the first difference is. Now the first difference, I don't know the first 2 arrows, but I know the second 2 because I know 7 minus 2 is 5, and I know 14 minus 7 is 7. Okay? So we take it down another level. Now, all I really know, I don't technically know these 2. All I really know is that 7 minus 5 is 2. I'm going to be like, yes, Ms. Visto, you should know that. Yeah, I know that. And I know it because I can see it in my data points, in my x and y, or my x, f of x, ordered pairs. It's quadratic, which means as soon as 1 second difference is 2, they all must be 2. And so this question mark right here with this 5 is going to make it 2. And this question mark with this question mark is going to make it 2. So knowing that, we can do some working backwards and find out what those question marks should be. What's going to be 2 away from 5? Well, we already took care of 7. I want to go the other way. So this should be a 3. And if I work backwards again, this should be a 1. So really, those numbers I know are going to be 1 and 3. Okay? Those are going to be 1 and 3. And that means that I can work backwards and kind of go back up into my table. -2 with this 1 right here, this is going to represent a +1 essentially. This is going to take me to -1, which is perfect because then -1 + 3 is actually 2. And how sweet is that? We've figured out that our missing value is -1. Oh, that was so fun. Okay, so we've identified whether they make a quadratic or not. Now, here's what we also need to identify. What is that quadratic function going to be? How can we write a quadratic function? Now, in order to do that, we need to solve for a, b, and c. That sounds a little funny, right? But we're looking for the coefficient on the x squared, that's a. We're looking for the coefficient on the x, that's b. And we're looking for the coefficient on the constant term, right, c. So we need to find a, b, and c. Here's how we're going to go about doing it. First of all, we're going to generate 3 equations. If we're looking for a, b, c, 3 variables, then we need 3 equations, right? It's kind of a rule. When we're working with systems, the number of variables you're solving for should equal the number of equations that you have, and vice versa. Then, we're going to use a method to solve for those 3. If you've got 3 equations, let's solve them. I'm going to show you with reduced row echelon form because I think that's awesome. I love that my calculator does that for me. Some of you like elimination? Great. Some of you are crazy and you're going to go Kramer's rule. That's a little OC, but you could probably do it. Okay? And then once you know a, b, and c, it's pretty easy to write the equation of the quadratic. You just got to plug in some information. So let's take a look. a2 squared plus b2 plus c equals 3. Now those 2's and that 3 came from this first ordered pair, 2, 3. The x value was 2, so instead of ax squared, I wrote a2 squared. Instead of bx, I wrote b2. C is c, kind of boring. And then my value, y, is 3. If I input 2, my output is 3. Same thing actually, if I input 6, my output is 3, because in the second ordered pair, it's 6, 3. And so what I'm plugging in now is I'm plugging in 6 for x, and it's got to equal 3. So a6 squared plus b6 plus c equals 3. In the last one, a8 squared plus b8 plus c equals -3. So, here we go. Now, I'm going to clean those up a little bit, and you should too, because that makes it a little bit easier to look at. That looks more like a system that we're used to solving. 4a plus 2b plus c equals 3. 36a plus 6b plus c equals 3. And 64a plus 8b plus c equals -3, right? Because that last order pair is a -3. Turn it into an augmented matrix. I told you I'm going to show you using RREF, reduced row echelon form. You have a choice, but to me, this is my favorite choice, so that's why I'm going this route. So 4, 2, 1, 3. 36, 6, 1, 3. 64, 8, 1, -3. So I plug that in my calculator, I punch in a 3x4 matrix, I get all my data, or all my entries, because that's a spot in a matrix is an entry. So I plug all my entries in, and then what do I get? Well, I get these 3 values for a, b, and c. Like, how sweet is reduced row echelon form, really? I love it. You should too. A equals -1/2, b equals 4, and c equals -3. Okay? So once I know those, look at, I found a, I found b, I found c. So now I'm ready to write the equation of the quadratic, which is so cool. Because that tells me that these 3 data points fit in this function, -1/2 x squared plus 4x minus 3. That is so cool. Okay, I'm sorry. I just love this. So, I wrote the equation because I found a, b, and c because I wrote my 3 equations with my ordered pairs x and y. So, your turn. Generate 3 equations, plug it into your calculator, do whatever it is you're going to do to solve, and then write the equation of the quadratic. Here we go. Plug them in. Is that what you got? Okay. Now that you've got them plugged in, I want you to try and clean them up a little bit. What would those equations look like cleaned up? Is this what you got? Careful in that first one. -1 squared is a +1. So 1a minus 1b plus 1c is -12. In the second one, 1a plus 1b, difference between -1 and 1 right there, plus c equals 0. By the way, that means 1 is a root or a 0 of this equation. Whatever the equation is, that 1 is going to be a solution. Then 4a plus 2b plus c equals 9. Did you write an augmented matrix? That should be your next step. If you want to use RREF, I'm not passing judgment if you want to use something different. By all means, do what works best for you. But if you go this route, pretty slick. It's going to tell you that a equals 1, b equals 6, and c equals -7. Our equation for our quadratic here is 1x squared plus 6x minus 7. Okay? Now we could totally factor this, find out that this actually is a solution. You could probably figure out that the other solution is going to be -7. That'd be kind of cool. Okay, we don't need to do that right now. Here is our quadratic. This quadratic fits these points. This is the only quadratic that these points lie on. It takes 3 points to determine a quadratic. Okay. Now, there's going to be some different cases where we're going to represent our data. Our data is not going to be a perfect fit onto a quadratic the way these ordered pairs were. Here's an example with some film. And I'm going to walk you through this example in your graphing calculator when you come to class. Okay, I got a great little walkthrough I want to show you, and we'll do it as all together in class so we can get it all figured out all together. It's going to be awesome. Okay, so we'll get that all figured out. In the meantime, though, I want you to be thinking about what did we do to write this? Make sure you know that process. And then, how did we do this? How did we identify a quadratic? How did we find the missing value? So can you identify? Can you write? And then when you come to class, we're going to talk about how we actually use regression on our calculator. We're going to use the quadratic button, a little bit different than what we used in the past. Okay? So you're going to be a professional. It's going to be awesome. Bring your calculator and we'll get it all totally squared away.